So let me start by thanking the organizers for setting up this program. So today I'm going to present results that have just appeared here in this paper, and also some sort of background work that we did in the past that motivated these studies. So I'm going to speak about permanent currents in cavity-qubit systems, and this is work in collaboration with Camille Aron from École Normale Paris, Sven, and Ilian Kapit. So our work is based on a recent, very fascinating experiment from the Google group and Santa Barbara, where they managed to create a ring geometry of qubits of basically, say, two-level systems with complex coupling between the two-level systems. And that complex coupling gave rise to an artificial gauge field. So approximately you can think of these qubits as anharmonic oscillators, and they sort of have this kind of Hamiltonian structure. With suitable approximations, you can show that there is an artificial gauge field here. So what they showed in this experiment is that they created a rather long-lived current of photons, meaning these anharmonic oscillators, going around in circles. So this is one result here. You see that you excite a qubit, or you can think of it as a photon, and then you have this circulating photon. So, what they can show is that they can show that you create these currents thanks to this artificial gauge field, and you see the results that the current keeps oscillating like this. And they also can have two excitations and have a hole in the opposite direction. So this was the first report of first experimental measurement of permanent currents, bosonic currents, in these systems. So, and depending on what your total field is, total flux is, you can have different scenarios. If you have a zero flux, then you don't have these chiral currents. So, however, these currents are not really permanently long-lived because of dissipation in the system. So the question is how to create indefinitely long-lived currents. So this is again some of their experimental measurements where you see that you have these kind of chiral currents for different parameters of the problem, and they can also measure the density matrix elements of your system. So now, since the system is subject to environmental effects, what happens is that if I create an excitation and I let it go, on a time scale of a couple of microseconds, it dies out because of dissipation in the qubit and so on. So the question is, what do we do? So we thought of an idea where one could have this kind of excitation, but also create a delicate balance between drive and the dissipation which is already there, to see if we can generate these indefinitely long-lived currents. So we strike a delicate balance to activate specific states which are capable of carrying currents. And this idea is usually called quantum bath engineering, and the idea is to create some non-trivial states in open quantum systems. And the sources of dissipation are qubit dissipation, cavity decay, and so on, depending on what your open quantum system is. And qubits are coupled with complex hopping. Each qubit is coupled to a respective photon mode, and photons are driven by a classical microwave drive. So this is the kind of setup we were thinking, which is a slight extension of the Google Santa Barbara setup, but it's not too far away from it. So the general idea is, on one side we have all these interesting Hamiltonians with complex couplings, with artificial gauge fields, and variety of various proposals of creating various kinds of Hamiltonian on one side. On another side, we have some past experience to create a delicate balance between drive and dissipation to create entangled states. Now, if these entangled states are such that they are capable of carrying current, and if we manage to unite these two ideas, then we are successful in having a system in ring geometry, creating entangled states, and since the entangled states carry current, we succeed in creating permanent currents. So in the past, we have been able to show that if I have two units, I can create entangled states between these two qubits by some suitable protocols, and this was already realized in collaboration with Irfan Siddiqui's group at Berkeley. And we wanted to ask how to put this to use in terms of permanently moving transport, in terms of permanent transport. So that was the idea, and we tried to see how we can bring these together. So I'm going to briefly explain this and quickly go to what we are, go to the latest results. So the general idea is basically you have a qubit in each cavity, and then there's hopping between the cavities. Question is, can I drive the system in a way such that I create a singlet state between the qubits? So notice that the qubits are not directly talking to each other. They are talking via the photon hopping. So this is an experiment that has been already realized in Berkeley. And what we did is we showed that by suitable construction of a Hamiltonian, and one can show that one can write an effective spin chain for the qubits and treat the rest of the things as the bath. And one can write a microscopic Hamiltonian for the bath, qubit coupled to the bath and cavity coupled to the bath, and then you have your system. And then one can show that by suitable drive, I can hit a singlet state. I can reach a singlet, I can prepare a singlet state which is indefinitely long-lived. So you switch on your drive, and the dissipation is already there, but you switch on your drive in such a smart way that the singlet is maximally occupied, and then you say that the system is entangled. And this proposal has been successful, and here we see a fair agreement between experiment at Berkeley and our theory, where you see that as we go in time, this is the probability of having a singlet, and you see that you get singlet with about 80% probability, which is considered very high in the field. So now the question is, and one can actually go to several of these qubit systems, not just two. You can think of three and think of a large spin chain, and try to devise protocols where you can go to any of the members of the first excitation manifold. So just for an example, if you have 3, then you can go to this state, which is a W state, which is highly entangled state. So now we wanted to see how we can take the setup at Berkeley, try to make a ring geometry of it, but at the same time make it similar in spirit to the Google experiment in Santa Barbara, and try to see if we can generate permanent currents. So the currents that were generated in the Google experiment are not permanent. They are long-lived but not permanent. And now we came up with a mechanism where we can drive this system in a way that you effectively create an entangled state in your ring, and that entangled state carries current. So if I hit that entangled state, then our job is done. You have permanent currents. And notice that these currents are truly permanent, because as soon as a dissipative term tries to bring it down to the ground state, you drive it, and there's a delicate balance such that your steady state is a entangled state. So, okay, so the Hamiltonian is, you have a couple of spins which are coupled to, in a complex way, the spins are coupled to each other. Each spin is coupled to a photonic mode, and the photons are driven. So that is the setup. The setup is each cavity is coupled to a qubit. Each qubit is inside a cavity, and the qubits are directly coupled with a complex coupling, and then the cavity is driven. Okay, so one can try to truncate the Hilbert space and work with the ground state and the first excitation manifold, and show that one can study the reduced density matrix of just the qubit sector and find an optimal drive that can reach a desired target state. So this idea is again called quantum bath engineering, where you engineer both the bath and the Hamiltonian to reach a desired target state. So that is an idea which originated around 2012-2013 from the Yale group. So this is, for example, an expression of what should be my optimal omega drive. What should be my drive frequency when I drive the cavity, and you basically can choose this kind of drive, and try to see if it gives you a desired entangled state, or and hence a chiral current. So here is a plot where the color is the current, and you see that if I sit at a given drive and a phase, the classical drive has a frequency and a phase, and you see that if I sit up optimally, I can generate a large permanent current, and so on. So this is what we showed, that you can generate a large permanent current by choosing your drive and phase optimally. So this is a result where if I have 3 qubits, I have 3 states in the first excitation manifold, k equal to 0, 2 pi by 3, and 4 pi by 3, and I can go to any of these states, and each of these states carry a current. So my k equal to 0 would correspond to this W state that I had written, and that carries a current, and the current is can be computed by any of these formulas here. Yeah. So let me just outline the basic principle here. So suppose I have 2 qubits, and this is my singlet state here, and this is my triplet 0, and these are the 4 states. So T minus is just down down, T plus is up up, and spin is up down minus down up by square root of 2. So the idea is that I drive the system such that I go here, okay? But in doing so, I will end up creating off-resonant drives like this, correct? In doing so, I'll end up creating off-resonant drives like this. But thanks to dissipation, my dissipation automatically brings me back here. So my dissipation actually should be greater than this off-resonant drive, but this dissipation should be much smaller than this drive. So there's a very delicate thing where you finally hit a desired target state. So that is the core of the idea which we exploited, and the conclusions are we have infinitely long-lived current, preparation of highly entangled states, and we actually have the dynamics of entanglement, how it reaches an entanglement state, and this was precisely measured in Berkeley for the 2-qubit case, and we hope to extend it to many qubits and cavities in general to study many body systems, and also some highly needed brute force numerical calculations that include both the qubits and the photons, and we also plan to go to higher excitation manifolds in your spin. Thanks.
In the context of the excitation, what you do, especially with respect to the non-resonant case, you would actually end up getting a long-lived state when you take it through the triplet state.
So it's a good question, and let me go back to this thing which is drawn here. So you notice that you go here, but you also generate the off-resonant term and try to go to triplet plus, but there's a dissipation inherently in your system which brings you down here, and this finally dissipation brings you all the way down here. So if I have an inequality such that gamma of T minus S, this rate is far, far greater than gamma, right? This rate has to be far, far greater than small gamma. Small gamma brings me all the way down, but my small gamma also has to be far, far greater than this off-resonant term. So this off-resonant term is gamma S2 T plus, because I don't want to go to T plus, because T plus is non-entangled. So
you'll have to just consider the phase lag in your when you're driving the system.
Right.
So how do you take into account? That's the
so the thing is you actually have these. You can have we finally calculate the expression for gammas. Just let me show you here. Okay, so you actually can calculate the expression for gammas and try to make sure that your omega drive is in such a place that this inequality is satisfied. Okay, and in fact that piece will also have the phase in it, so you can sit at a place where this inequality is satisfied, and that inequality is possible in experiments. That was the thing. So yeah. And also one comment I wanted to make is that since you can change both the drive and the phase in experiments, you can really switch back and forth between the two states. And that's something we are thinking about, yeah.
The current is a is a quantum coherent phenomenon because of the phase that you have put in, right?
Right.
Like an Aharonov bomb phase or
something. Right, exactly.
Complex.
Exactly. And just to elaborate on that point, these are photons, but the way you have this artificial phase is that experimentally they can create a time-dependent coupler, and then finally you can write down a Hamiltonian like this: e to the I pi j k, aj dagger a k.
Right.
Okay.
Right.
Yeah.
Right. I got slightly confused. You had started out with 3 harmonic oscillators. You actually did not need 3, right? You can do it with just 2 qubits, two-level systems coupled, which is what you did later.
So
is there a connection between the 2 models?
So the first, the Google experiment I showed was technically 3 qubits, but the way you understand the qubits is effectively as anharmonic oscillators. So there you just had 3 qubits. So to think of currents, I need at least 3. But to think of entangled states, 2 are sufficient. So just to be clear, when I spoke about singlets, just 2 is sufficient. And that was the Berkeley experiment. But to speak about currents, I need at least 3. And that was the Google experiment. But the Google experiment was not for a driven system. You just create excitation and let it go. Yeah, that is possible, but in these cavity-qubit systems, to my understanding, no one has done. But in terms of maybe parallel quantum dots or in terms of quantum dots, I think maybe there are experiments. But yeah. So, yeah. At least in this system, 3 was the minimum.
Okay, let's thank the speaker again.